For years, the cybersecurity community treated misinformation as a localized problem. The goal was a classifier sharp enough to identify and quarantine a single string of text, like a fabricated article, before it reached a user. Large language models have expanded this threat surface beyond the reach of a single classifier. Adversaries now utilize LLMs to coordinate simultaneous attacks across the entire architecture of an information platform. A single prompt can execute a multi-layered campaign, mutating the surface text of a claim, spinning up simulated users to mimic organic engagement, and injecting false data into the external search databases that fact-checkers rely on. Even a highly accurate classifier looking for syntactic errors or known falsehoods is unable to detect these peripheral manipulations. By the time an algorithm analyzes the core claim, the surrounding social proof and corroborating evidence have already been weaponized to ensure the content bypasses algorithmic moderation. Misinformation is increasingly a pervasive security challenge. Treating it strictly as a content generation issue leaves a system with a structural vulnerability. To audit and secure these modern pipelines, engineers require a structural framework that maps exactly how language models interact with our information systems. This requires a try-roll framework. Within any given ecosystem, LLMs operate across three simultaneous identities. First is the attacker. Here, the model is misused as an engine for infinite generation and adaptive camouflage, producing deceptive material at zero marginal cost. Second is the defender. Platforms deploy their own models as automated reasoning agents and scalable fact-checkers to filter out the attacker's output. Third is the victim. This is the critical blind spot, where the defensive verification pipelines themselves fracture under adversarial pressure and become targets. These three roles are not static. They function in a continuous loop of exploitation, detection, and adaptation. Designing a security protocol that accounts for the attacker and defender while ignoring the victim role leaves the pipeline vulnerable to internal exploitation. To map these threats, we plot the three roles against four layers: content, social, evidence, and workflow. At the intersection of attacker and content is content camouflage. Adversaries rewrite claims, separating deceptive meaning from surface cues. By mathematically adjusting sentiment and phrasing, the attacker strips away the linguistic artifacts that classifiers are trained to flag, rendering the lie invisible. But unamplified camouflage has zero reach. The threat must expand into the social layer. To spread the camouflaged content, adversaries deploy reinforcement learning-based bots to execute long-horizon strategic campaigns. Learning specific engagement patterns, these agents mimic human timing and behavior to evade detection. They execute this behavior to trick a specific defensive architecture, graph neural networks, or GNNs. GNN-based defenders look past the text and analyze the mathematical structure of how a post spreads to identify botnets. This makes the social structure itself the primary target for camouflage. Adversaries instruct their models to generate strategically timed engagements, carefully mutating the propagation graph to avoid the structural anomalies a GNN would detect. At this layer, LLMs synthesize the exact behavioral metrics that modern structural detectors require to grant a post legitimacy. Moving deeper into the matrix, we reach the evidence layer.
This is the critical bridge between external reality and automated reasoning. The defensive mechanism here is retrieval-augmented generation, or RAG. The defending LLM pulls facts from a trusted external corpus to verify claims. But this creates a severe vulnerability: knowledge poisoning. Attackers silently flood this corpus with synthetic evidence corroborating their lie. Using a tactic called retrieval visibility enhancement, adversaries manipulate search parameters to guarantee that the defending system retrieves their poison data over legitimate sources. The defender LLM ingests this corrupted text, unaware its foundational premise has been tampered with. It processes the poison data, outputting a persuasive hallucination. By successfully polluting the evidence environment, the attacker forces the defending model to become the engine that legitimizes the misinformation. There is a dangerous assumption in software engineering that integrating an LLM as an autonomous fact-checker provides security by default. That assumption ignores the final row of our matrix, the victim role, where the verification workflow itself becomes the primary target. This chart shows research distribution across the roles.
The green line and the small 15.9% green slice highlight a critical blind spot. Meanwhile, massive red bars show industry focus heavily skews toward attacker generation, leaving defense pipeline vulnerabilities unexamined. One of the most effective ways to compromise a pipeline is through an LLMs judge prompt injection. Adversaries embed hidden instructional payloads deep within the poisoned evidence files we discussed earlier. When the RAG process retrieves that file, it pulls the malicious instruction directly into the system's core processing environment. Agentic workflows, systems granted the autonomy to browse the web or trigger external tools, compound this vulnerability. A single injected error propagates across multiple autonomous steps. These attacks bypass semantic filters. They do not argue with the system. They directly hijack the logic and action space of the defending agent. Treating a language model strictly as an infallible defender ignores its inherent structural vulnerabilities. It provides adversaries a backdoor directly into the verification pipeline. This role layer framework maps the complete threat landscape. With this matrix, we can establish 3 strategic imperatives to harden the ecosystem. First, engineers must move past static detection accuracy. Measuring how well an algorithm identifies an isolated string of false text is no longer a viable security metric. Defense must shift toward budgeted ecosystem-level risk evaluation. This means measuring the exact computational cost and adversarial effort an attacker must spend to successfully corrupt a fully scaled social evidence pipeline. Second, LLM-centric workflows must be systematically hardened against evidence poisoning. Retrieval systems need stringent verification protocols for the external data they ingest before they process it. Third, platforms must mandate auditable, human-in-the-loop verification checkpoints for high-stakes assertions. In practice, this means building a hybrid architecture. The automated AI network operates at scale to filter structural anomalies, but defers final truth validation to human operators when confidence thresholds drop. Autonomous defense systems are not yet fully resilient against autonomous attacks. Securing the information ecosystem requires integrating structural AI safeguards with human oversight.